Okay, so the next one is about Newton's second law of motion, and it's going to ask us to define it. So the crucial part is, well, his first law, we said, is the law of inertia. If the forces are balanced, then the object will move at a constant speed or stay stationary. And I taught you that as objects that are staying still want to stay still, objects that are moving want to keep moving. And we've got this idea of law of inertia for the first law. The second one is just make sure you're happy with your my fat auntie triangle. That'll just take you all the way through all of these, really. So what is Newton's second law of motion? Well, when the forces are unbalanced, another way of saying that is I have a non-zero resultant force. So if it was a positive, moving forwards, negative, moving backwards. So when the forces are unbalanced, the object will accelerate according to, and then we're just going to mention that A equals F over M. Done. So now we've got one here. We can see what's the force to accelerate, and I've got a mass here. So clearly I need my fat auntie formula, and it's asking us for what force. So I want that. F equals M times A, mark. F equals the mass, there's the mass, 60 kilograms, times the speed 3, no unit changes there, and that's going to equal 6120 equals 180, tick, and then the unit newtons. Next one's some tricky ones now, so moving to higher demand, we can see we've got a unit change on this one. So we've got kilonewtons, so that's times 1,000, equals 2,850 newtons. And then we've got an acceleration there. So I've got a mass, I've got an acceleration, and it says that's the force. So my fat auntie, it says what is the mass? So I'm after that. M equals F divided by A, mark. That's going to equal the force. And we've got to remember to use the unit change. So that's 2850 divided by the acceleration that we're given, 2.13. I'll get a calculator because bear with me. 2850 divided by 2.13 equals 1338. So it equals 1338.02 and lots of other numbers, but I'm just going to change my pen colour there. So if you're ever to leave that there without fully reading the question, it says I want 3 significant figures. So there's the first, there's the second, there's the third. I'm now going to look at the number behind to see if I round up or round down. So that needs to round up to a 4, 1, 3, 4, and obviously that 8 turns to a 0. And then we're ready with our unit kilograms. Okay, next one. It says the same car as above. Now that's a clue. Anytime it says as above means you probably need to use some information from the question you've just done. If I just change my colour here, let's go with, that's quite pleasant, we'll go with that. So we've learned that we've got a time there, t. We've got what's the final velocity, so v. It's from stationary, so that's u, and it tells us the acceleration, but the tricky part is I've got to go up there to find it. There it is. So I'm just going to move that down and write that under there, 2.13 meters per second squared. So we've learnt in class a equals v minus u over t, but I want to get v on its own. Well, we can see what's going to happen, and for some of you, I taught you maths in year 8. Well, the first job is let's deal with the division first. So I'm going to multiply both sides by t. That they cancel. So I can now say v minus u equals at. And you can see I've just moved that to that side and all this over here. And then, well, I don't want the u there. Minus the u. So I'm going to go add u to both sides. And I'm left with v equals at plus u. Now what we're going to see is we don't really need to worry about the u because stationary is 0. So u becomes 0, so I don't need to write it. So I'm just going to rub all of that out. And again, you can play the video back if you're struggling with that rearrangement. I'm just going to go, well, v equals at plus u. Now I can substitute the values in. V equals the acceleration, 2.13, multiplied by the time, 12 plus 0. So get my calculator, 2.13 times 12. The final velocity equals 25.56 meters per second. So tricky question. I think you'll do well with that. Right, next one. This is really important. So I've said to you, the trolley experiment, where we measure the velocity here. This is u. The velocity here, v. And then we'll use the light gates to find the time. And we know that a equals v minus u over t. But this experiment, we're adding a force and we've got a mass. So we can use this equation and the my fat auntie. So what makes this tricky is we've got these two sorts of equations interlinking here. So it says, well, the first part is, why do we use light gates to measure the acceleration? Well, they increase, I better not do that because you might do it in a test. So they increase the accuracy. If you wanted to, I'll use the word precision. They increase the precision. Why? Well, because they remove human reaction times. So they increase the accuracy. This removes error from human reaction times. It says, how could the force acting on the trolley be increased? Well, there's the force. This is the force over here. Well, clearly I've got a weight hanger. So the best thing to do is to add some weights, well, as we know, using my wrinkly gran. And you can see why they like this so much in the exams. We've got all of these formulas interlinking here. So this force, or the weight, is just the mass times gravity. So I can just say in there, add weight to the hanger, add mass to the hanger, because in this example, they're not going to take marks off you. So how could the force on the trolley be increased? Add weight to the hanger. Next part then. Well, when we do this, let's imagine we were hanging 50, 100, 150, and we plotted this graph. So we got that result, we got that result, and we got that result. And we can see as we hang more force, oops, I wanted to just move that down. I'm going to rub all of this off. So what we're saying is I'm increasing the force there. I'm going to rub all of this off as well. The mass is going to stay the same. I'm not changing that. And what's going to happen is as I increase that force, the same mass, we know that the acceleration equals the force over the mass. So if this is going up on top, the acceleration is going to go up. And we can see that. As the force increases along the bottom, the acceleration goes up and it's a nice straight curve. So it says using the graph to the left, and I'll change my colour now. Let's pick something that stands out a little bit better against that red. I'm going to rub that off. So I said we're increasing the force and this increases the acceleration and we've got a linear relationship. They're directly proportional. So it says calculate the mass of the trolley. Well, again, we're going to need the my fat auntie. And it says calculate the mass. So M equals F divided by A. And then I've just got to pick a force and pick an acceleration. Because it's a straight line, wherever I pick on this line, it's going to give me the same gradient. So, and the gradient here is going to be the mass, which is kind of nice. So I'm going to treat myself to nice easy numbers, 102. So there's the force, 100, divided by 2, and then, so my mass, that is a 50 kilo trolley. I wish I'd used better numbers because that's a very big trolley. But hopefully that makes sense. Well, the next part is it says draw a line to show a lighter trolley. Well, a lighter trolley with the same forces applied, 50, 100, 150, is going to accelerate more. So all I've got to do is draw a straight line. There, this would be a lighter trolley. If I had a heavier trolley, it's going to be more difficult to accelerate. That would be a, oh, that's terrible. That would be a heavier trolley. and that ends Newton's second law of motion. But please make sure you revise well on the F equals ma acceleration. It's a tricky practical with lots of interrelated equations, but with loads of practice you'll get really good at it.